We are going to start this section without the word all right. We're going to talk about derivatives as rates of change. So this is basically just one giant section on applications. We're going to talk about approximating changes with tangent lines. We're going to talk about marginal cost and how like some business and economics applications. We're going to talk about population growth and speed, velocity, acceleration, that stuff. That's what we got in store, just using a bunch of the stuff that we've already learned. So not a lot of new stuff here. These videos are mostly going to just give you some extra context for the math that we've already done. All right. There it is. There's the all right. So let's start by recalling some things. All right. I'm going to give you the right side of an equation, and hopefully you know what this represents. F of a plus h minus f of a all over h. So this right here should speak out in your mind, or maybe it's in a slightly different format, as an average rate of change. All right, it's the average rate of change of the function at a and h units after a. All right, that h is just how far apart these 2 points are that we're looking at for this average rate of change. And of course, this is very, very, very similar to the derivative at a, which is almost literally the same thing, but taking the limit as h goes to 0. Right, the derivative is just the average rate of change as the 2 points get infinitely close together. H, right? H is that distance between the 2 points. So that's how we're going to start, and we're going to talk about how to use this. So if we kind of combine this, if h is small enough, and there's a lot of mathematical conversation about what small enough means for different functions that we're not going to get into here. But if h is small enough, then these 2 things are basically the same. Like if h is small enough, then we can approximate the derivative and the right-hand side as basically being the same thing. So look at that. I'm just kind of copying down that last line. The derivative becomes about the approximate average rate of change. They are close because the derivative is just what happens to the rate of change as we get really, really close together in these 2 points. F of a plus h minus f of a all over h. All right, so the last thing that we're going to do with, we're going to start really going to get close to the punchline of this part of the video. Okay, and that's basically saying, how can we estimate really close to one function value if we don't actually know the other function value? So if we only know things about a, how can we say things about places after a? And that's going to be taking this last piece and just solving for this quantity right here. This is what we're really going to look for. So let's multiply both sides by h. And if we do that, we're going to get h times f prime of a equals f of a plus h minus f of a. And we're solving for that other quantity, so we're going to add an f of a to both sides. And we're going to get that an approximation, say we only know things at one point, like right now, say, I don't know what's going to happen to the population of Olympia right now, but I know the population of Olympia right now, and I know how fast it's growing. Well, then we can use this approximation to guess things about the future. And there's a couple of uses for that we're going to get into later on in this section as well. So that's going to be f of a plus h times f prime of a. So if we want to approximate something close to a, so this is right, h units more than a, If we want to know how the function behaves, we can approximate it by saying, look at where we're at, and then add some multiple of the derivative. So to kind of give a little picture of what's happening right here, let's look at tangent lines. Remember, the derivative of a function is just the slope of the tangent line. So f prime is the slope of that orange line right here. So say we don't know anything about the future. We only know something about a. And we're looking a little bit in the future, so we're adding an h to our input value. Well, you know, most things aren't a line, so we're really just approximating with the tangent line. The difference here is just going to be the error. And notice that, hold on, what I'm really trying to say is, let's look at if this slope is like -2. If the slope is -2 of this tangent line, then we can approximate 1 unit in the future. The slope is -2, that means down 2 over 1. So that means that we would go down 2 and over 1, which is really just exactly this. The slope is like the down 2 part. The h would be like the over 1 part. Well, let's do some examples. I want to make that a little bit more clear. We'll talk about that in these examples. We'll talk about where this formula comes from. If f of 3 equals 2 and f prime of 3 equals 5, estimate f of 3.2. So if you wanted to, you could just plug in the formula and don't have to worry about it. But I think conceptually it's interesting to think about the connection to the graphical interpretation. So we're going to do both in this example. So the formula says that we should have boxed this. Let's box this. We can approximate a point a little bit in the future by just looking at the function value that we know and multiply by the slope. So again, let's copy down that formula. F of a plus h is approximately equal to f of a plus h times the derivative. And let's see how this applies. So a is the point that we know. So what point do we know? We know things about this function when x is 3. And h is just how far in the future are we looking? How far into the future from 3 are we looking? We're looking at 3.2, so how far ahead is that? Not 0.3, it's 0.2. And if we wanted to look in the past, we could have h be -0.2. So f of a plus h, that is just f of 3.2. And that's going to be approximately equal to f of a plus h times f prime of a. F of 3, we know f of 3 is equal to 2. We know f prime of 3 is equal to 5. Now all that's left is adding things together, and we get 3. Okay, so we can approximate the function value. We're really close to 3, and we know what it is at 3. When x is 3, we're at 2, and the slope is 5. So if we move ahead, if the slope is 5 and we move ahead 1/5, we have an increase of 1. Increases from 2 to 3. Graphically, to kind of try to connect this to that thing that I was commenting on earlier, is we know we're at the point 3, 2. And we know the slope is 5. So the slope is pretty steep. So specifically, right, if we moved, the slope is rise over run. Slope is 5 over 1. Rise over run. So something else on the tangent line would be the point 4, 7. Right? If we move up 5 units up to 7 and move right 1 unit up to 4, that would be a slope of 5. But specifically, we don't care about going all the way to 4. We were only looking at 3.2. That's like 1/5 of the distance. So if we're only moving 1/5 of the distance, how high up do we move? 1/5 of the distance. So this slope of the blue is also 1/5, right? For a line, the slope's going to be the same no matter where you are, right? We could go up 10 over 2, up 5 over 1, up 1 over 1/5. So that's all this formula is really doing. We're just approximating using tangent lines. And in fact, we could go one step further if you wanted to. We're done with this problem. The equation of this tangent line is y minus the y value of 2 equals the slope times x minus the x value, which is 3. And so if another way to approximate at 3.2 would really just be to plug in 3.2 into this equation. Add 2 to both sides, plug in 3.2. Look what's happening. It's the same exact calculation. So we could approximate it with this new formula I gave. Sorry, I'm circling the wrong thing. We could approximate it with this new formula. We could look at it graphically as an approximation with tangent lines, or we could look at it analytically, approximating with tangent lines. The idea is what we're doing to start this section is saying, let's say we don't know what this function is, either in the future or in the past. We only know it at one point. Well, we can I'm pointing on my other monitor. We can approximate it with a tangent line. And then lines are very easy for us to work with, and we can use that to approximate a little bit in the future or a little bit in the past. It's just a method of approximating. And again, the applications of this method will be done in the next couple videos. There's a bunch of different ways to kind of conceptually understand what we're doing here. And we're going to do a little tease, okay? I think that it's the 4th video that we really talk about this some more. But a little tease of this. If C of x represents the cost in dollars of producing X units. Oops, I didn't specify this. Cost in dollars of producing X units. And we say C of 30, let's say C of 30 is 5,000. And C prime of 30 equals 50. So it wants us to estimate C of 32 and interpret. So we can do this, again, the exact same way. All right, we're going to use that same function, that same formula, if you will. We're going to approximate this cost function, which we don't know, with the tangent line. So this is the formula that we're using to approximate things. And again, everything here is different. For example, our function is no longer called f. Our function's called c. A is the input level that we know. We know things about a production level of 30 units. And h is how far into the future or how many additional things we're doing. We're looking at 32. Well, that's 2 more than 30. So we can really just use this formula in this way to say C of 32 is approximately C of 30 plus 2 more times the slope, which is 50. And you plug everything in, you're going to get 5,000 plus 100, which is 5,100. So that's an estimate of the cost of producing 32 units. And that would be the end of our answer, right? Is writing this out in words. You know, so the cost of producing 32 units is about $5,100. Okay. Or in other words, it costs about $100 extra to produce 2 more units. That's going to be related to a concept called marginal cost that we talk about in, I'm pretty sure, the 4th video. Yeah, the 4th video. Okay, that's our final answer. Let me know if you have any questions, and good luck.